Okay, we'll be doing 4.2, and I'll do some review questions from section 4.1. So let me share the screen right now. So I was done with 4.1. Beginning 4.2, I'll lecture on that for a while and go back and do some review problems. The section 4.2 is on something called the mean value theorem. So I'll need to show that to you from the text. And so 4.2, the mean value theorem. It's on page 287. We start off with something called Rowe's theorem. Okay, so Rowe's theorem, let me put this on your cheat sheet if you wish. So it says let f be a function that satisfies these three hypotheses. These are givens, sort of like the givens in geometry proof that you did in high school. There's the given and then proof. Hypotheses are the givens. So let f be continuous on a closed interval from a to b, and let f be differentiable on an open interval from a to b. So closed here, open here, and f of a equals f of b. That means the same height, same y coordinate at a and b. Then there's a number c in a, b, between a and b, such that f prime of c is equal to 0. This is called Rowe's theorem. Here's a picture of what it may look like. Okay, so as you can see, these three pictures here, continuous and differentiable. Actually, four pictures here. Okay, so continuous, differentiable. Each one, you can take a slope, and same height at the beginning and at the end. So look at A and B, A and B, A and B, A and B. F of A equals F of B, same height. F of A, F of B, F of A, F of B, F of A, F of B, same height. Okay, the theorem says then somewhere between A and B, they call it a C, such that F prime of C is equal to 0. Slope is 0 somewhere. Okay, here it's 0 everywhere. Here it looks like it's here. That's what they call C. Here's an example where you have two possible C's, one here and one here. They call it C1 and C2. And here's an instance where there's 1. But you have to have at least 1. You can have more. But somewhere between A and B, the derivative is equal to 0. Okay. So in the first problem, number 1, so they give us this graph here. Verify that f satisfies the hypothesis of Rowe's theorem on the interval from 0 to 8. Okay, so if we look at the graph, it looks continuous, differentiable. So differentiable means you can take a derivative, you can take a slope. Everywhere you can take the slope of a tangent line between 0 and 8. Okay. And f of 0 is equal to f of 8. F of 0 is 3. F of 8 is also 3, same height. Okay. So somewhere between 0 and 8, the derivative is 0. So they want you to estimate those values to c. So it looks like there's one over here at 1 and one over here, which is 1, 2, 3, 4, 5. Okay, so the c values, we would say, are 1 and 5 for question number 1. Okay. Now, so that these verify that the function satisfies the three hypotheses of Rowe's theorem on a given interval, then find all numbers c that satisfy the conclusion of Rowe's theorem. Okay, so number 5, f of x equals 2x squared minus 4x plus 5 between -1 and 3. Okay, so let me show you that. Now, this function is clearly differentiable everywhere. How do I know? You can take the derivative, 4x minus 4. In fact, we're going to need that in just a second down here. Okay. Since it's differentiable everywhere, it's automatically continuous everywhere because differentiability implies continuity. If you have a differentiable function, it's automatically continuous. And if it's continuous everywhere, it's certainly continuous on the closed interval from -1 to 3. It's differentiable everywhere, therefore it's differentiable on open interval from -1 to 3. So those are the first two conditions for Rowe's theorem. And f of a equals f of b. They have to be the same height. So f of -1, plug in -1, 2 plus 4 plus 5 is 11. So -1 comma 11. Plug in 3, f of 3 is 18 minus 12 plus 5, which is also 11. Okay, so there it is. So the three hypotheses of Rowe's theorem have been satisfied. Showing that to you again. We have continuity on the closed interval, differentiable on the open interval. and f of a equals f of b, same height. Okay, at both endpoints, the height was 11. Again, you can put all that on your cheat sheet. So there's a c somewhere between -1 and 3, such that f prime of c is equal to 0, and they ask you to find it. So no big deal. Take the derivative for x minus 4, set it equal to 0, and that's an easy algebra, x equals 1. So the c value is 1. And yes, 1 is between -1 and 3, so that's perfectly fine. Okay. Here's the next one, number 9. What does number 9 say? Let f of x equal 1 minus x to the 2/3. Show that f of -1 equals f of 1, but there's no c in open interval from -1 to 1, such that f prime of c is equal to 0. Why does this not contradict Rowe's theorem? Okay. So what does that mean? So at the two endpoints, you have the same height. F of -1, plug in -1, 1 minus -1 to the 2/3. 2/3 means square, and then take the root, okay, power over root. -1 squared is 1. Cube root of 1 is 1, so I have 1 minus 1, which is 0. Plug in 1. Well, we already know 1 raised to anything is 1. 1 minus 1 is 0. Okay, so it's true at the two endpoints. F of -1 equals f of 1. But they're saying there is no c between -1 and 1 such that the derivative is 0. Well, let's try it. What's the derivative of this function? Derivative of 1 is 0. Derivative of negative x to the 2/3 is -2/3 x to the -1/3, which can be rewritten as -2 over 3 x to the 1/3. Now, I would set that equal to 0, but that's impossible. Okay? A fraction is equal to 0 when the numerator is 0, but the numerator is already -2, so it can't happen. Okay, so why does it not contradict Rowe's theorem? Well, as you can see here, this function is not differentiable everywhere. It's not differentiable at x equals 0, right? You can't plug in 0. 0 does lie between -1 and 1. Okay? So it violated the condition that be differentiable from -1 to 1. Okay? So there was no c, so no violation from number 3, but the violation was from number 2. The function was not differentiable everywhere on the open interval because the function is not differentiable at 0. Okay. All right, that's that. Now I will show you the mean value theorem. Page 288. Mean value theorem. Let f be a function that satisfies the following. F is continuous on a closed interval from a to b, differentiable on the open interval a to b. That sounds exactly like the previous page, Rowe's theorem. Number 1, same thing, continuous on a closed interval. Number 2, same thing, differentiable on the open interval, but there was no number 3, f of a equals f of b. So the two endpoints can have different heights. They don't have to be exactly the same. So what's the conclusion of the mean value theorem? There is a number c in the interval from a to b such that f prime of c equals f of b minus f of a all over b minus a. Now that looks scary, but that's essentially just the slope of the line joining the two endpoints. Okay, so you have f of a and f of b being different heights, perhaps. Well, you can figure out the slope. Somewhere between a and b, that slope is attained. The derivative is equal to the slope of the line joining the two endpoints. And here's a picture of what it might look like. Okay, continuous, differentiable. Continuous, differentiable, function in black. But f of a and f of b are different heights. Different heights. So this has some slope. Okay, just for teaching purposes, let's pretend the slope here is -1/2. Somewhere between a and b, the slope is 1/2. So there's a picture of what they have. See that this is parallel to this. Likewise here, all right, f of a and f of b, different heights. So here's a slope. Looks like it's positive. Let's pretend I say 1/2. Somewhere the slope is exactly 1/2, like this, and like this. And you can really think of the mean value theorem as Rowe's theorem on its side. If you kind of turn your head a little bit and look at it like this, and you say, oh yeah, it kind of looks like Rowe's theorem. Slope is 0, slope is 0. And if you turn your head the other way here, slope is 0, slope is 0, slope is 0. Or, if you think of it this way, pretend it's hard to do because you know there's a book and you know I'm turning the book. But if you can temporarily ignore that I'm turning the book and just kind of focus only on that, it looks like Rowe's theorem, right? It kind of looks like, oh yeah, slope is zero, slope is zero. It's pretty much Rowe's theorem on its side. In fact, if you were actually going to prove it, which they go over here, I'm not holding you responsible for it, but to prove the theorem, you actually use Rowe's theorem and do exactly what I was suggesting. This one, if you kind of ignore the book, ignore the fact that I'm tilting it, and if I angle it like this, you might look at it and say, oh yeah, slope is zero. Somewhere the slope is zero, Rowe's theorem, and there it is, and there it is. Okay? So the mean value theorem is just Rowe's theorem on its side. Okay, so for number 3, now we're using the mean value theorem. Verify that G satisfies the hypotheses of the mean value theorem on the interval from 0 to 8. Okay, so continuous everywhere, differentiable, right? Differentiable means I can draw a tangent line. Okay, so satisfy. B, estimate the values of C that satisfy the conclusion of the mean value theorem on the interval from 0 to 8. Okay, so from 0 to 8, I will connect these two. So watch what I do with my ruler. I'll go this side. So I'm going to join that point, beginning point, to the ending point. There's a slope. You can figure out what it is, but you don't really need to. It looks like it's about 3/8. Okay. Somewhere on the graph, that slope is the same thing. And what I'm going to do is just move my ruler up or down, something like that. Okay. And I'm going to say that's a possibility. So C is equal to 2, or C1 is equal to 2. And I'm going to do the same thing coming down. If I join, I'm joining these two endpoints, and then just slide it down this way until I get a tangent. Okay, so it looks like I got this point, roughly. So where is that? 7. Okay, so my two values that I will pick are 2 and 7 for B. C, estimate the values of C which satisfy the conclusion of the mean value theorem on the interval from 2 to 6. So only going from 2 to 6, 2 to 6. So only look at this portion of the graph, forget the rest of it. Okay, so 2 to 6, I'm going down. Okay, so I'm going to connect these 2 points with my ruler and do the same thing. Okay, so this point and this point, kind of joining it like so. Okay, and I'll just go up until it looks like I get a tangent line. So roughly it looks like it's over here. So where's here? If it's 4, 1, 2, 3, 4, yeah. Okay, so that's the idea behind that one. All right, so mean value theorem now, questions here, 11 and 13. I did 13, you do 11 on your own. Verify that the function satisfies the hypotheses of the mean value theorem on a given interval. And find all numbers C that satisfy the conclusion of the mean value theorem. Okay, f of x equals natural log of x from 1 to 4. Natural log of x is differentiable everywhere because the derivative is 1 over x. We know that. So therefore, it's automatically continuous, and therefore it's differentiable and continuous on the interval that you need. Okay, so for 13, f of x equals ln x from 1 to 4. It's continuous everywhere it's defined, so that means it's continuous on bracket 1, 4 and differentiable on parentheses 1, 4. That's all the hypotheses you needed, the givens. Okay, so what I'm going to do is find the slope. So f of b minus f of a divided by b minus a, f of 4 minus f of 1 divided by 4 minus 1. Plug in ln 4 minus ln 1 divided by 4 minus 1. Natural log of 1 is 0, so I have ln 4 over 3. That's the slope. Not a very nice number, but still a slope. Okay, so the mean value theorem says somewhere between 1 and 4, that's the slope. Okay, so let me take the derivative, which is 1 over x, slope in general, right? 1 over x equals natural log of 4 divided by 3. I can reciprocate both sides. If two things are equal, the reciprocals are equal. Flip that, you get x. Flip that, you get 3 divided by ln 4, which is approximately 2.16. Okay? And 2.16 is between 1 and 4. Not exactly right in the middle, but it doesn't have to be. So it works. Okay, and 15, find the number C that satisfies the conclusion of the mean value theorem on a given interval. Okay, technically you don't have to graph it, but I graph it just for teaching purposes. Let's just find it. So f of x equals radical x on the closed interval from 0 to 4. Okay, we know it looks like this. We can take its derivative. So it's differentiable on open 0, 4 and continuous on bracket 0, 4. Okay. So somewhere there's a C, which is the slope of this line. Okay, it turns out to be 1/2. So they tell me to go from 0 to 4, plug in 0, 0. Plug in 4, 2. So you're going from 0, 0 to 4, 2. That slope is 1/2, right? 2 minus 0 divided by 4 minus 0. 2 divided by 4, 1/2. Somewhere the slope is 1/2. Okay, so take the derivative. The derivative of radical x, that's x to the 1/2. 1/2 x to the negative 1/2, which is 1 over 2 radical x. Set that equal to 1/2. A little bit of algebra. X equals 1, or C is equal to 1. Okay, you can tell when you plug in 1, that works, right? Square root of 1 is 1. So you get 1/2 equals 1/2. So the ordered pair is 1, 1. So right here at 1, 1, the slope matches the slope of the line joining the two endpoints. So right here, the slope is 1/2. Notice it's not exactly in the middle. Halfway between 0 and 4 is 2. Okay, the theorem doesn't say it's exactly right in the middle. It's just somewhere between 0 and 4. So right here, slope is 1/2, parallel to this line with a slope of 1/2. Okay. All right, and that's that. And then the rest of the class, I took some problems from section 1. So let me go over those for you. So back in section 1, okay, 37 was asked for, find critical numbers. So h of t is t to the 3/4 minus 2t to the 1/4. Okay, so take the derivative. Derivative is 3/4 t to the negative 1/4. And then negative 2 times 1/4 is negative 1/2. T to the negative 3/4. Okay, clean that up a little bit. Put that in the bottom, put that in the bottom. 3 over 4 t to the 1/4 minus 1 over 2 t to the 3/4 equals 0. And I notice right away, t equals 0 is automatically a critical number, right? Critical number means when is the derivative 0 and when is the derivative undefined. It's undefined at t equals 0. But h of 0 does exist. I can plug in 0 here and here. So it's in the domain, but you can't put it in for the derivative. So t equals 0 is automatically a critical number for my final answer. Now, how do you set this equal to 0? Okay, let's clear the fractions. Multiply by 4t to the 3/4 on both sides. Okay, 0 times that is still 0. Okay, this comes out to be 3t to the 1/2. 4 cancels out. T to the 3/4 divided by t to the 1/4 is t to the 2/4, or 1/2, and I still have the 3. Minus 2. 4 divided by 2 is 2. That t to the 3/4 cancels that t to the 3/4. Okay, I set that equal to 0. Move over to 2. Divide by 3. Square both sides. So that gives me 4 9s. Okay, so my critical numbers are 0 and 4 9s. 41, f of theta equals 2 cosine theta plus sine squared theta. So the derivative is negative 2 sine theta plus chain rule 2 sine theta cosine theta equals 0. There's a common factor of 2 sine theta. So factor out 2 sine theta. Negative 1 plus cosine theta equals 0. This product equaling 0 means either sine of theta is 0, or this thing equals 0 means cosine theta equals 1. So on a unit circle, sine of theta equals 0. When is the y coordinate equal to 0? That's here and here and here and here. So multiples of pi. Cosine of theta is 1. X coordinate is 1. That's over here, but that's already swallowed up by this. So I just want multiples of pi. So theta is equal to k pi, where k is an integer. Okay, 43. F of x equals x squared e to the negative 3x. Okay, so product group and chain rule. So f prime first times the derivative of the second, e to the negative 3x times negative 3, plus second function, e to the negative 3x, times the derivative of the first, which is 2x. Set that equal to 0. The common factor of x e to the negative 3x. X e to the negative 3x, x e to the negative 3x. If I take this out from here, I have left over a negative 3x. And if I take this out, I'm left with 2. Double check by multiplying it, right? This times this is negative 3x squared e to the negative 3x. Yep, it's all there. And this times 2 is 2x e to the negative 3x. Okay, so either this is 0, which means x equals 0. This is 0 is impossible, right? E to anything is always positive. That can never equal 0. And this one gives me 2/3, a little bit of algebra. So my critical numbers are 0 and 2/3. Okay, and finally, 57 was asked for, find the absolute maximum and minimum over the given interval. So 2 cosine t plus sine of 2t between 0 and pi over 2. Now, in order to differentiate and work it out, it's better to not have a double angle. So I use the identity that sine of 2 theta is the same as 2 sine t cosine t, sine of 2t, I should say. Okay, so that's the same as that. You don't normally want to mix up a double angle with a regular angle in the same problem. Okay, so f prime, derivative of this is negative 2 sine t. This looks like it involves the product rule. So 2 sine t first times the derivative of the second plus the second cosine t times the derivative of the first, 2 cosine t. All right, and I set that equal to 0. And so clean it up, negative 2 sine t minus 2 sine squared t plus 2 cosine squared t equals 0. All right, at this stage of the game, you want to get it down to just a single trig function. And usually when that happens, you go with the majority. Majority wins. Right now, there's more sines than cosines. So I should make this be forced to become a sine, rather than going the other way around. If you have more sines, why should the sines change, right? Change the one that has fewer. So cosine squared was 1 minus sine squared. Okay, that's piggybacking off the identity sine squared of t plus cosine squared of t is equal to 1, which means a little bit of algebra, cosine squared t equals 1 minus sine squared t. Okay, so distribute this stuff out. Negative 2 sine t minus 2 sine squared of t plus 2 minus 2 sine squared of t. These two combined to give me negative 4 sine squared t minus 2 sine t plus 2 equals 0. Factor out a negative 2. Take out a negative 2. 2 sine squared of t plus sine t minus 1 equals 0. So this is a quadratic equation in sine of t. Negative 2. 2 sine t minus 1 sine t plus 1 equals 0. So in other words, if you multiply this back out, you get this. Okay, so either this is 0, impossible. Either that, or this is 0, or this is 0. Set this equal to 0, you get sine of t equals a half. Set this equal to 0, you get sine t equals negative 1. Okay, sine of what nice angle is a half? That's pi over 6, right here. Does that lie between 0 and pi over 2? Yes, it does. Sine of t equals negative 1. You're down here, you're at the south pole, but that's not going to give me an angle between 0 and pi over 2, so forget about it. All right, so I try pi over 6 and the 2 endpoints, okay, to do problems involving closed intervals, right, the closed interval method. You always have to check the endpoints and the critical numbers. Okay, so 0, pi over 2, and the critical number of pi over 6. Okay, plug in 0 back here. Cosine of 0 is 1. Sine of 0 is 0. So I get 2 plus 0, which is 2. Plug in pi over 2. Cosine of pi over 2, cosine of 90 degrees, that's 0. Plug pi over 2 here, you're taking the sine of pi, that's also 0. 0 plus 0 is 0. And then at my critical number, which is pi over 6. Plug in pi over 6, pi over 6. Cosine of pi over 6, x coordinate, it's not a half, so it's radical 3 over 2, plus sine of twice the angle, so 2 times pi over 6 is pi over 3. Sine of pi over 3 is radical 3 over 2. Okay, and very fortunately, these already have a common denominator of 2, so 2 radical 3 plus radical 3, 3 radical 3 over 2. And if you were to punch it in a calculator, it is bigger than 2. Okay, so minimum, maximum. So I'm going to go with the absolute minimum being with pi over 2 comma 0, and the absolute maximum at pi over 6, there's a 6 there, comma 3 radical 3 over 2.